All right, so we're going to start the presentation. I'm going to talk about two infrastructures we developed in our company. I'm going to show the infrastructures. If it will interest the community, we'll integrate the infrastructures inside the open source project. It's two completely different infrastructures. I just happened to show them in the same time slot. So let's start because we don't have too much time. So I am a senior engineer at HPE. Been developing since 2004. Started developing in the army, in the Israeli army. These are my my email and LinkedIn if you want to contact me later about any of the subjects. So this is the agenda. Let's just jump right in. So I talked with some people here, and everyone have a different picture in mind when I'm talking about the term counters. So I wanted to start by showing a log file of how will the system look after counters are implemented in it. So you will have your normal log file, your normal log prints, and in a configured interval, you will see all your counters. What changed, what incremented, you could see that. So these are the counters we're going to talk about today, this type of counters. So why do we need counters? Systems with high-frequency events that want to log these events in a certain way, they can't really use log prints, right? If I have, let's say, like in this example, let's say I have a certain event that happened 37,000 times in the last minute. I can't have 37,000 log prints. It won't be practical to write all these events in the log. So when I have high-frequency events, counters will help me show this, monitor these events in a much better way. Most of the time when you have high-frequency events, you use log debug or log trace. And when your normal system is running, you won't see these log prints, right? Only if something happens and then you change your log level to debug or trace, and the effects are only from this point and beyond. You can't see what happened in the past, right? That's the next bullet. Let's say someone contacts you for about a production system that is currently running, and there's a certain bug. The system is in a problem, in an error state, and you want to troubleshoot what happened in the system. So in this type of system, like a controller that has thousands of packetings, flow installation, only counters will actually help you understand what happened in the system that caused the problematic state. Also, it can help you analyze bottlenecks. I will show this in a few slides. I will show how can I analyze bottlenecks using counters, what events happen in my system until now, and analytics. I will show you examples of all of this. So you have to think of pure Java. Our implementation is not wasn't made for ODL. It's not MDSAL or something like this. We use the same infrastructure for. It's just a Java utility. We use the same infrastructure for different type of software, and you can just integrate it into your code. It's a very lightweight infrastructure, very easy to integrate it. I will show some code examples for that. Counters is not something we invented. There are other third parties that allow you, that give you counters. We support all the common use cases for counters. And as I said, we already used this implementation in previous products, and it was found to be very extremely useful for monitoring and troubleshooting systems. So these are the capabilities of our counter infrastructure, incremental and state counters. I will elaborate elaborate about it later. You can configure the interval for when to print the counters to your log file. You can silence some counters because the counters are integrated with your log library. You can silence the counters as you silence log prints. It has almost no overhead on the system. You can query the current state of counters using regular expressions. Let's say you have 200 different types of counters in your system. Now you want to know, give me all the counters that are related to switch. Give me all the counters that are related to packet ins. So you can query based on regular expression with the name of the counter, and we exposed REST API for that. So, okay, this is a code example for a normal incremental counter. So let's say I have a class, it's called user service, and I have a method, user event. It's a high frequency event. It's called 5,000 times a second. If I would add a log line there, it won't be practical, right? I would have 5,000 log prints per second. It's not practical. So the only thing I need to do is change this log line with a counter increment. And this will take me to, will bring me to this state. So the counter incremented here. This is an example of a log file using this counter. So as we see, I configured the counter to print the delta of the counters each minute. For the interval is 1 minute. So we will see the normal log output, and we will see every 1 minute the times this method was called. The alternative would be 37,000 prints in that minute. So of course, it's not practical. Of course, the infrastructure is, the purpose is to support how many counters that you want, right? So you can have 50 different counters. So in this example, we see that other counter was incremented 72 times, and after 1 minute, it wasn't incremented at all, but a different counter called foo counter was incremented 17 times. Remember, the alternative is just log prints for that. So this is an example how you actually define a counter group in your code. This is 95% of this code is just boilerplate that you copy paste. The only interesting thing here is the names of the counters. As you can see, we defined 3 different counters here. User event code, this is the counter that we've seen previously, and 2 other counters. The other code is basically copy paste. And that's it. So our current implementation supports two types of counters, incremental counters, as you've seen before. This counter is manipulated using normal increment, and the log prints show the delta from the last log print. If there was no delta for the counter, there will be no print. The other counter is a state counter. You manipulate its value using a set. You set the value. And if the counter value has changed, you will see it in the counter print. This is very useful for detecting queue buildup. So let's say every time I add or remove an item for a queue, I will set the current size of the queue into a counter. And then if I'll have a buildup, I will see this counter actually showing up in my log prints. As I mentioned before, because the counters are integrated with your log library, so you can silence a counter as you would silence a log print. Let's say the counters are defined by, how do I put this? Yeah, no, I mean, the counter are integrated at the log as info, so if I want to, if there's a class and I don't, let's forget about counters. If I have a class, I have some log prints in info level, and now I don't want to see them anymore, so I just go to my log4j file, and I would write the full class name and change it to warn, right? This is how I change the severity of this specific class. So it's the same thing with the counter infrastructure. You can just silence a counter like this in the same log4j file, for example. So this is a use case. How do you use counter to identify bottlenecks? Let's say I have a method. It's called myBusinessLogic. It's doing three things. It goes to the DB and queries something. It sends something on the socket, and it calls a very CPU-intensive method. So the scenario is I know that this method is called 5,000 times per second. And I also know that the output of the method is only 2,000. I only get 2,000 results per second from this method. So I understand that something is slowing me down, but I want to know what is slowing me down. So using the counters, I can easily add a counter before and after every step here from the 3 steps. I created 6 counters here. This is how it will actually look like. And in the end, I will look at my log file and we'll see the differences in the numbers. So as you can see in this example, before DB was called 5,000 times. That's obvious because it's the first thing that is called. After DB is called 2,000 times, and the rest of the counters also obviously increment only 2,000 times because the effect remained. So I know the DB is slowing me down in this example. And this would be an alternative result. If the CPU intensive method would be slowing me down, I would see 5,000 on every counter until the after intensive counter that has the value of 2,000. Now I know that the intensive method is slowing me down. So in a few seconds, I easily detected what is the bottleneck in my method. This capability gives you a lot of power to detect bottlenecks. Can you see the picture here? Okay. Yeah, not so much. So what events happened in my system until now? Let's say your system is running for a month. You have, I don't know, 500 different types of counters for different different use cases your system supports. And you want to get something happened, there's a problem or something like that, and you want to get like an overview of what events happen in my system. Let's say I would have a counter if a DB query failed, if a DB insert statement failed, if a switch failed and I had to recover it, something like anything. Using this API, this is just REST API, right? Using this REST API, I could get like a quick overview of all the events happened in my system in the last few weeks or ever since the system started running. There's no alternative for this with log prints, right? I wouldn't go looking at all my log files in the last 4 weeks to understand what happened in my system. And another very strong capability is analytics. We have an RRD tool, a round-robin database. We just load it with the counters value every 1 minute, 10 seconds, whatever interval you want. And afterwards, we can create, the RRD tool actually creates graphs of all the timeline of the counters changes. So let's say I had a spike at a certain point, I would see this. This gave us lots of useful information for production systems that we couldn't get in any other way, like RX packets, TX packets, anything. Just turn it on, it takes the free.
Also can give Okay. It can also give you correlation between events. For example, if you see a drop in the RX and you see some configuration changes or other counters increasing, you can easily do the correlation over graphs instead of seeing numbers and log lines. So that's a very powerful capability using counters.
The RRD tool graphs are integrated with the project, or this was done manually, separately?
Yeah, it's separate, but it's very easy to it's
Yeah.
very easy to integrate. This is the main purpose of RRD databases.
And how do you get the counters from OpenDaylight to RRD tool? So you're just parsing the logs? Okay. So ODL has SNMP project. Do you think it would be interesting to expose the counters with SNMP, as there are still a lot of NMSs that are consuming SNMP, and it would be easy to integrate with
So
monitoring
maybe
system?
you want to answer?
Regarding SNMP, you will need to define a different MIB for each counter. So that's the biggest problem regarding this option. So it's not straightforward translation.
All right. So just under the hood in 3 bullets, we based the solution using Java's atomic long and atomic integer. This incrementing these objects causes really insignificant overhead to the system. We're using enum semantics instead of, let's say, some other third parties. If you want to define a new counter, you need to register it or use a config file to register new counters. So as you've seen in the first example, we just use an enum. It's really a copy-paste from an existing counter. And we have a background thread that runs in the background and writes the delta of the counters to the log in each interval that you configured. So as I said, we didn't invent the concept of counters. There are third-party alternatives that already give you counter capabilities. These are some of the known third parties. We haven't made a deep comparison between our solution to these solutions, but our solution is very lightweight. So that's it. So any questions regarding counters, or we will jump to the next infrastructure? All right. Gal, you want to answer that? Why did we choose our implementation?
At the beginning, we didn't see or have any third party. It was a couple of years ago. And after several years of using this specific infrastructure, we got to a certain balance of the output and the usage of this infrastructure, which really didn't change a lot from the beginning. And we just gained the experience in production with it. So that's the actual reason.
Any other question? All right. So now to a completely different infrastructure. The async infrastructure. All right. So historically, in hydrogen, every OSGI bundle used the bundle activator pattern. You can activate OSGI bundles in, I think, 3 different ways. In hydrogen, every bundle used the bundle activator pattern. It extended a certain activator class that ODL written, I think. And in the Activator, you would declare your implementations, you would declare what other services you depend on. So that's what happened in Hydrogen. After the transformation to MDSAL, the plugins and or applications started defining their dependencies, implementations, and API using Young model, and it would auto-generate the RPCs and the notifications by itself. So this infrastructure was written in the Hydrogen version, and if the infrastructure still interests the community, we might do some adaptations to it to fit the current use of bundles. But as you can see in this picture, let's say I have two applications. So currently using MDSAL, the communication between the applications supposed to go through MDSAL. But what if I have a fat application that wants to break some thread calls inside of it, right? So application A is created here. It consists of two OSGI services. The communication between those OSGI services is not defined by the ODL community, right? It has nothing to do with Young model. It's not even have to be OSGI services. You could use POJOs or whatever you want. Right? But let's say it is written using OSGI services. Our current infrastructure, async infrastructure, is ideal for this type of implementation. The red arrow in the middle says unwanted because we understand that all communication between applications today is supposed to go through MDSAL. But theoretically, because we are running inside an OSGI environment, this communication could, the red arrow in the middle could use our infrastructure as well. So this is an overview. This is an example of an application A. The application implements packet processing listener, so any incoming packet will be notified to service. Service A here implements packet processing listener, so on packet received will be called on service A by MDSAL upon every packet in. And let's say that this application is consisting of 3 services, and they call each other when a packet is received. Service A calls service B calls service C. So this is how okay. I'll go back a few steps. All this infrastructure, the goal of the infrastructure is to save time for the developers, so the developers could focus the coding on the business logic of the services, and they don't have to think about asynchronous capabilities, asynchronous boilerplate code, thread pools, producer threads, consumer threads, I'm talking about like a normal Java call, right? Service A is getting a packet and is calling service B in a normal Java method invocation. The developer who wrote this code don't need to think about asynchronous code, right? He's just invoking a method. So let's say service B, his method is just invoking service C. So we have this normal chain of Java calls. And with this infrastructure, I could convert these calls to asynchronous calls running in different thread pools, just by changing the configuration file. All right, I don't need to touch the code at all. So how do I do this? So this is the configuration file. Let's say I'm defining a new thread pool. It's called our thread pool. It has 8 threads, and I'm saying service B will run all the calls to service B will run in this thread pool. I can define a worker count, so it means service B will use up to 5 concurrent threads. Service C will use up to 6 concurrent threads. And by doing this, I transform the calls you've seen before to asynchronous calls without changing the code at all. So how did it work, right? This sounds like magic. It doesn't sound at first place. If it was POJOs, actually we couldn't do it. Just because the services used to be based on OSGI services. So when you register an OSGI service to the OSGI registry, we kind of hijack this registration, and we actually register a proxy. So the invocations aren't actually made on the real service. They are made on the proxy. So as you see, when service A called to do something on service B, it actually called it on a proxy. And the proxy put the call into a dedicated queue that was created for service B. The infrastructure, the red parts here are all done by the infrastructure. The developer didn't do anything here. So service B took the call, it put it in the dedicated queue, and also we configured the number of worker threads, right? So the worker threads are sitting on the queue and listening on it, and when the message gets into the queue, they invoke the actual do something on service B. So this is what happened under the hood, but from the developer perspective, he didn't touch the code. He just called service A, just called service B. So the benefits of this is the developers can focus in coding the business logic of the service. The API didn't change. It remained exactly the same using the help of proxies and reflection. You could dynamically change the name of the thread pools, the size of the thread pools, the affinity between the services and the thread pools. The developer didn't need to write any bug-prone boilerplate code for async method invocation, right? Usually, if you wanted to do what I just illustrated here, you would have to write a queue and put the message inside the queue, and there would be, you have to create some consumer threads. They would be pulling the queue, maybe write some synchronized block. This code is actually kind of a boilerplate code, right? If you want to convert a method call to an asynchronous method call. A small caveat here, the code obviously must support multi-threaded execution. So if the code in service B uses a hash map, and the developer of service B would just use a normal hash map and not a concurrent hash map, and now 5 threads execute the codes simultaneously. So obviously it won't work, right? Service B the data structures in service B have to support multi-threading. The queue that we've seen before, the dedicated queue, can be kept. The infrastructure allows this kind of API. And when, let's say, the producer is much faster than the consumer, we could theoretically get a memory leak, right? I'm making much more calls than I'm producing more calls than I can consume, so the queue will just increase and increase. So by having a kept queue, I can drop the exceeding messages, and I would prevent the memory leak here. So this is another benefit that, you know, sometimes when you write the code yourself, you forget about it, then you get a memory leak, then when you analyze the system, you understand, oh yeah, the producer is faster than the consumer, I found my memory leak. So this infrastructure helps you do it. So as we said, I magically transform service B calls to asynchronous calls, right? But I might not want to convert all of service B methods to be asynchronous. So you could just add this annotation that we created. This will tell the infrastructure, these methods should run in the caller thread, not in the new thread pool. So having all this magic really helps us invoking the services in a remote ODL. If the calls are asynchronous, what do I care if they run on this ODL or another ODL? I mean, if I wanted to run it on a remote ODL, I could do it with the same infrastructure. I would just have to call the line in bold here, set target, and I would have to put the IP I want to contact, the IP of the remote ODL. And then under the hood would look like this. So as I said, we're actually invoking do something on a proxy. The proxy calls our service, our remote async service. This is a class that we created that helps us do the remote calls. It calls a ACA sender, and then, as you see, all this happens in ODL number 1. The ACA call goes to ODL number 2. And then it really resembles the previous example. We reach the proxy in ODL 2. We go to the dedicated queue of the service, and the call gets to service B that actually resides in ODL 2. So this was very easy because I just showed you a unidirectional call, right? What about replies? Most of the time when we're talking about bidirectional invocations in asynchronous code, the reply is a future or a listenable future. And we really wanted to keep the code clean from this kind of Java utilities, right? Because as we said before, the infrastructure wanted to, the developer doesn't know that the API is asynchronous API when he writes it. So, so here, to allow the bidirectional invocation, service A had to implement a new interface. This is the name of the interface, for example. And the reply and he implemented the reply method. Service B had to add a new field, a reply handler, and when do something is invoked, he actually tells the infrastructure, get me the caller. I want the next. You see the 2 lines in bold, right? So the first line determines where the call will be invoked, and the second line is the actual invocation. So what's the caveats of what I just showed you? By keeping the code clean from the async Java utilities like future and listenable future, we lose their capabilities, right? If if the API of do something would be future, we could look at the result and use future get with timeout or future is done. This is capabilities that you get when you use the future, Java's future. Of course, that's a trade-off. When you want everything to be seamlessly asynchronous, you can't really do this. With the current implementation of the infrastructure, the reply code must contain the async util set target. Currently, let's say a developer will open a code and he will see this. It kind of looks like magic. Like, what's that call? Async util set target. It looks like magic, right? So that's another caveat. We might fix this in the future. So, and a bit under the hood, how we implemented this. So this is actually our, in a hydrogen version, you used to activate your bundles. You used, as I said in the beginning, you use the bundle activator. You would extend some kind of activator. I don't remember the name. So if you want your bundle to use our async infrastructure, you have to extend our activator. And normally, and just as you did before, you would declare your implementations and your dependencies. And as I explained before, the infrastructure, this point really allows the infrastructure to hijack the registration of the OSGI service and register a proxy instead of the real service. It also, this is the point where it creates the dedicated queue for the service. An object for the queue to be multi-purpose for any API call, we just use the Java's reflection. So the queue is actually holding an object of this type, method called message, that holds the method and the arguments. And if some of you that looked that ever implemented invocation handler, this is proxy in Java, you get the method and the arguments on each invocation. So we just use this for the items in the queue. This is how we know which method was invoked and what are the actual values of the arguments. And we also create dedicated worker threads and assign them to the thread pool you configured in the configuration file. The worker threads are pulling the dedicated queue in a loop. On every message, they just invoke the method using Java reflection. Java reflection, since I think Java 5 or Java 6, reflection is the overhead of reflection is much less significant than it used to be. In the older Java versions, reflection would cost you a lot, making all the solution a bit expensive, right? So using the illustrated capabilities, we actually harvest the proxy and reflection power, and we allow seamless conversion of normal method invocation to asynchronous method invocation or remote, if we want this. That's all I had to say about this infrastructure. So if the infrastructure will interest the community, we will see what adaptations we need to do to the infrastructure to fit the current community needs. We've seen some capabilities we think that are absent in the current MDSAL solution. Customization of thread pools. Let's say an application wants all of its notifications to run on a specific thread pool. Today, it would have to code it itself, right? I'll take you back to the slide that showed it. Just a second. All right. So now I'm not talking about the infrastructure. I'm just talking about what extension can MDSAL do for the RPCs and notifications. So let's say application B wanted to listen to a packet in notification. We think that when I registered in MDSAL to listen to this type of notifications, I can tell MDSAL, okay, when you call me with this notification, I want you to call me in a specific thread pool. I don't want to do the thread pool myself, right? The same goes for RPC. Let's say I want to tell MDSAL, when an RPC is invoked, I want to invoke it in a dedicated thread pool. We work a lot with the OpenFlow plugin. So the OpenFlow plugin implemented, when you call install flow, you want to install a flow on a switch. They implemented a thread pool of hard-coded 10 threads that will invoke all the install flow, remove flow, update flow. And this capability is something basic, and it could easily be integrated into MDSAL, in our view. That's it. So, do we have time?
Yeah. Yeah, just one more thing. You should consider using this infrastructure if you have a FAT application. Many POJOs in your bundle and communication between the POJOs, the Java logics. This can make your life easier, organizing your code in that application and allowing you to hold higher performance and break your code into different threads.
Well, actually, if they wrote the code using POJOs, they can't harvest the infrastructure. They have to convert it to OSGI service calls.
Yeah, exactly. That's one of the points. I mean, this infrastructure should not be used only in applications that originally used activators. Activators in OSGI, yeah. But also, if you have a FAT application, I'm not sure you'll be able to maintain it for long. I mean, it will grow. You'll have performance issues. You'll want to break it into different services from within your code, your application. So basically, it's a good pattern to be used in such application.